Okay, we're going to talk about a very special type of property today, and that's called a colligative property. Now, a colligative property deals primarily with solutions, and when we're talking about a colligative property, we're talking about the addition of a solute that changes certain physical properties. Now, the important thing to remember about a colligative property and what separates it from other properties is that a colligative property, it changes the physical properties, but it doesn't matter what you're dissolving, just how much of it you dissolve. And the more you increase whatever you're putting in there, the more you increase the effect of that particular colligative property. Now, the four colligative properties that we're going to examine are boiling point elevation, freezing point depression, vapor pressure lowering, and osmosis/osmotic pressure. The last two kind of going together. Now, when we're talking about boiling point elevation, we're talking about adding in a solute, and that solute addition causing the boiling point of the solvent to increase. So in this first picture over here at the left, you have just a system of your liquid solvent. Now, at which point, if you hit the boiling point of that particular substance, it will cause evaporation and vaporization to occur. However, when you add any solute, what you're going to do is you're going to resist. Think about the solute, the red particles in the second picture, as being tiny little barriers that prevent that ease of access out of the top of the beaker. So the more solute you add, the more little guardians you add to the top of that, the harder you make the escape route of that particular solvent. The equation that we use to calculate this is that delta TB, the change in the boiling temperature, is equal to Kb, which is the molal boiling point constant meaning we can find it on a chart, times the molality times I. And I is actually a measure of how many pieces the solute breaks apart into when you put it into water. For example, if you put something like glucose, C6H12O6, into solution, it will not break apart. Therefore, the I factor of this is 1. However, if you take NaCl and you place it into water, it will break into Na plus and Cl minus. Therefore, the I factor for this is 2. We'll be working some calculations with this in class as we figure out our puzzle. Very similar to the boiling point elevation is the freezing point depression, except it's in the opposite direction. So the normal freezing point of water is 0 degrees Celsius. By adding any solute to that solvent, though, you actually decrease the point at which ice or water will freeze, by basically resisting the coming together of the molecules. And so the a similar equation exists for that of freezing point depression as it does for boiling point elevation. And we'll talk about this and work this in class some more. A real-life example of this would be the application of salt to ice on the roads during the winter months. When you add the salt to the road, you're not actually causing the ice to heat up. Instead, what you're doing is you're actually changing the freezing temperature at which that water becomes ice. So let's just say the ice is sitting there at -1 degrees Celsius, which under normal conditions would make water a solid. The addition of a great quantity of salt, a solute, will actually decrease the freezing point to, say, arbitrarily something like 5 degrees Celsius below 0. So if our new freezing point was -5, and the temperature of that H2O was -1, then it has not reached its new freezing point of -5. Therefore, it would be a liquid. To us, it would appear as if it had melted. However, all we've done is not heat up the solution. We've actually just changed the point at which it freezes. And here are a set of charts that you may want to record into your notes of certain boiling point and freezing point molal constants. And again, we will work with these in class some more. Vapor pressure lowering is also very similar to these in that there's always a certain amount of vapor pressure taking place. So think about a glass of water that you fill up and put on the counter. That glass of water over time will lose volume. Not because it's getting very, very hot in your house, but because naturally there's an interaction between the atmosphere and the liquid in there on that border. So at all times there's pressure from the air pushing down and pressure from the water molecules pushing up, creating tension, creating pressure here, and thus releasing some of that water into the vapor. When we add any solute, what we do is we dissolve that solute, creating a solution. Inevitably, some of those solute particles end up at the surface, thus preventing the amount of water from interacting with the air in the same way, thus lowering how much is able to interact and escape. The last colligative property that we're going to look at is osmosis and osmotic pressure. Now, in biology, hopefully you learned that osmosis is the movement of water across a semi-permeable membrane. Semi-permeable meaning it allows some stuff through, but not everything. So what we need to really focus here on is the concentration of the water molecules. So if you look at the left compared to the right in this diagram, look at the concentration of the water molecules. There's a greater concentration of water molecules on this side here. Therefore, solvent particles will move across the semi-permeable membrane to the less concentrated side. What this results in is a change in the amount of pressure due to the movement of water, thus osmotic pressure. This is an overview of the colligative properties, which we will discuss in greater depth and practice with calculations in class.